welcome to the next talk. My name is Kevin Wolf, and my co-presenter is Max Reitz, and we will be talking about the changes that we have made in the block layer in QEMU recently. There have been some pretty major changes, and we're going to tell you about how to use the block layer in its new state. But before we start with that, I have an announcement for you. We will have both sessions in the afternoon. And if you have a topic to propose, here's the board. In the next break, just come here. Paolo already made a start with a proposal, so you have a template. Just come here and write your topic. And now Max will start with the actual talk.
OK, so in the title, Managing the Block Layer, there's two parts. Or managing the new block layer, there's two parts. First, managing, and secondly, the new block layer. So first, we'll have to start with what the new block layer actually is. And that is going to be part of my part, the user management part, whereas Kevin will talk about how QEMU makes sure that you as the user don't mismanage. So let's talk about what the new block layer is. So this is what the block layer in general is. Inside of QEMU, you have some guest, which of course wants to store its data somewhere in a persistent manner. And so that this data is actually stored persistently, it has to be stored on the host somewhere. And the block layer is there between the emulated guest devices and the host storage to make sure that the data actually arrives there and that it later can be read back. So it has a couple of duties it has to fulfill. First, it has to read and write data from and to host storage that is outside of QEMU. It has to interpret image formats on the way. And since we already have all this data flowing through it, we can do things with it. Like we can encrypt it, we can do throttling, we can data duplications, all of these things. And for the implementation, this is split into so-called block drivers. And every block driver fulfills one of these tasks. So we have protocol drivers, which access host storage. We have format drivers, which interpret image formats, for instance, the QCOW2 driver. And we have now also filter drivers, which do data manipulation, such as the new throttle driver, which is throttling, or the quorum driver for data duplication. At runtime, this is represented in a data flow graph. And each data flow graph, of course, has some nodes in it. And these nodes, we have two. And each node is managed by some block driver. So data comes in. The block driver modifies the data in a way that is appropriate. And then the data comes out again. Of course, the data flow is bidirectional because you want to read and write data at the same time. But still, we can have some hierarchy of parents and children based on the fact that we have basically some kind of bus master in our system where the requests originate from. Usually, that is the guest device. So the guest device generates requests, sends them down to the first node in the data flow graph. And thus, this node then does something with that, generates new requests, hands them down to its children, and so on. And finally, at the bottom, we arrive at the protocol nodes, which do not have any other child nodes, but which access host storage. So they put the data outside of QEMU or get it from outside of QEMU. And then usually, you have your data stored in some form of image format, so you also need a format node on top of that, and then you can have all kinds of filters if you so desire. So this is a rather simple block graph because it's just linear. So let's make something more interesting. Let's make a block tree. So this is a rather simple example of a block tree. We have on the left side the same as we had before. Like we have a format driver on top, a QCOW2 driver or a QCOW2 node. And then below that, we have a protocol node, which accesses host storage. In this case, the protocol node is a file node, which means it will access any file on your host system, just on your normal file system. And this node is called the file child of the QCOW2 node because it stores all the main information of the QCOW2 file. It stores all the metadata, and it stores the data that is actually stored within that file. And the QCOW2 node then interprets the image format and can hand all the actual data up to its user. In this case, it does not have any user. It does not have any parent. So it doesn't do much at this point. But it can, QCOW2 nodes can also have a backing child. So in this case, it has one, which is, in this case, a raw file. So we need a raw format driver. Or actually, technically, it's a filter driver, but not that important. And this raw node, of course, also needs a file child, which manages the actual file that is physically stored somewhere. In this case, it's stored on a network block device. So we need an NBD node. You can see that every child has some name which corresponds to its role. So usually the main child of a node is called the file child, and the backing child is appropriately called the backing child. Then each node can also have a name. The QCOW2 node at the very top is named foo. Then we have a node called foo protocol, a node called bar, a node called bar protocol, and all these names can be specified by the user, and they're called node names appropriately, and you can use those to later identify and specify nodes in this graph if you need to modify it or if you need to start new operations on the graph. Then the QCOW2 node is the root node because it does not have any nodes as its parent, which also means that it's not very useful because only parents generate new requests, so there won't be any requests in this graph, so it will not actually do anything. So let's root our tree. That's connected to a guest device. The guest device is not part of the core block layer, so that means it's something we call an outside user, so it needs to have some interface between the actual block layer and between it. And this interface is called a block backend, which is just an internal object inside of QEMU, which connects any external user, such as guest devices, to nodes within the block layer. We'll come back to that later on. Now, note on filters. Filters are rather new in the block layer. They're different from format nodes. We've already talked about why protocol nodes are different. Protocol nodes are interesting and different because they don't store any data or they don't have any children inside of the block layer, but they store data outside of QEMU itself. So that's why protocol nodes are different from format and filter nodes. Filter nodes are different from format nodes in that they don't have any metadata. And that means you can stack them arbitrarily. In theory, you can also stack like a QCOW2 node on top of another QCOW2 node, and then you have a QCOW2 file inside of a QCOW2 file, but that just doesn't make much sense, and you cannot stack that arbitrarily. It just doesn't make sense. But if you want to, you can stack a throttling node on top of another throttling node if you have two throttling groups that you want to combine. So you can do that, and it makes much more sense. Or you can have different filters which you stack on top of each other. Like you can have the quorum node, which duplicates data, and then put throttling onto one of its children, and then put throttling on top of it. So you can do arbitrarily large configurations with that, which can be arbitrarily complex. And this is why you need to manage it. Because in the olden days, you just had probably a format node on top of some protocol node, maybe some backing chain, and that was rather simple. So QEMU could basically figure out what you want to do based on a single file name that you open. But now you can have very complex trees, so you need to manage every single detail if you want that. And this is the first thing we'll have to talk about, how you can construct these trees, or generally these block graphs. Then how you can modify them at runtime. Say you have some throttling that you introduce at startup, and that you later want to revoke again. That's, of course, something where you need runtime modification. You have some throttling node, you want to take it out, or you want to add a new one. And finally, the thing is that, as I said, these are all things you do, and you can probably do a lot, but you can, of course, also do a lot in a wrong way. And QEMU now has op blockers, or has better op blockers than before, to make sure that you don't do it the wrong way and that everything still keeps safe and you don't accidentally corrupt your data. And this is what Kevin is then going to talk about. So let's talk about how you can construct a block graph. The most simple graph, of course, is just a single node. So let's start with that. To configure a node, you just give QEMU a list of options or a dictionary of options, and it will then construct the appropriate node. The first thing you have to pass is the name of the driver that will manage the node, of course. And the second thing you can pass if you want to, sometimes you have to, is the node name, which you can use to identify the node later on. Sometimes it's mandatory, so you probably just want to specify it all the time. If not anything else, then because it gives you more options to manage everything. If you don't specify it, QEMU will auto-generate one, but yeah. Depending on the driver, there are also driver-specific options. For instance, if you create a file node, you have to give it a file name that the file node should then open somewhere on your normal file system. And it has some more options, which are not interesting to us now, but you can look them up in the QMP reference. So to create a very simple protocol node called protocol node, managed by the file driver, you would just give these options given here in JSON format. So you specify the driver to be file, you specify the node name to be protocol node, and the file we want to open is called foo.qco2, so we pass that. And then if you give that to QEMU, it will create this single node. Now, a single node is not very interesting, so let's make a tree out of it. Incidentally, we can see it's a QCOR2 file, so let's just create a QCOR2 format node on top of it. To create a QCOR2 node, you need the file option. This is a QCOR2 specific option. Actually, any format node has this option. And it's a reference to another node that you want to use as the file child. The QCOR2 node also has some other options which you can, again, look up in the reference if you want to, but which are not important to us now. There are two ways you can reference another node. One is by node name. So to create this QCOR2 node, which sits on top of the protocol node, you would simply, again, specify the driver of the node to be QCOR2, the name to be format node in this case, and as the file child, you would just pass the string protocol node. And then QEMU will create the format node on top of that protocol node, which you have already created. Another way to specify nodes is something we call inline specification. So instead of a string, you would pass a JSON object for the file option. And this JSON object then contains all the information QEMU needs to construct the child node. In this case, the protocol, the file node. And let's say, just for fun, we don't specify a node name here, and then you can see that QEMU will generate a node name such as hash block 042. And then it will create this whole tree. So in this case, you would not need to create the protocol node beforehand, but you can just create it with this single specification, which you can see how this can be extended to an arbitrarily large tree. And to pass this JSON information to QEMU, there are basically two ways. The first one is the blockdev-add QMP command, where you just pass the whole JSON object for the arguments option, and that's it. Then the tree gets created. Nothing special to it. If you're on the command line, then there's the -blockdev option, which also just takes a JSON argument, which is just JSON option, just the JSON object, and with that you can create just the very same trees. So actually rather simple. Of course, it can get rather long, so but that shouldn't be an option for management tools, which probably are the main users for this. And finally, of course, now you've created this tree, but it's not very useful because it just hangs around in the air and the root is not attached to anything. So let's attach it to a guest device, which we first have to create using, for instance, -device. And for any block device you create with -device or with device-add, you have this drive option. And for that option, you just pass the node name of the root node, and then QEMU will automatically connect that node to the guest device using a block backend in the middle. So you don't have to worry about that block backend. QEMU will just connect them automatically and do all the rest. You may remember -drive, which was like the big thing to configure all your block devices and construct your whole trees and things like that. Now you just shouldn't use it any longer if possible. Probably even if it's not possible, you should very much think about not using it any longer. There are a couple of reasons why. This is just some selection, and then the space ran out, and I just decided not to think of any more. But one important thing is that it does not correspond directly to the QWOPI schema. For all this block dev work, we have a very strict QWOPI schema, which specifies exactly which options you can specify for which block driver, which types they have, and so on. And -drive does not really care about that. It just takes all the options and then passes them in the block layer and tells it, do what you need to do with that. So that's not very good. It also has some options which conflict with the options we have for this schema. Like it has a file option, which obviously conflicts with the file option you can use for format nodes. So that's rather bad. It also has format probing, which is a security issue. So that's not too nice too. So all in all, it's kind of a monstrosity. It has a bunch of options, and it tries to figure out what you want by just looking at them and tries to do the best of it, which is not so good. -blockdev instead looks at the options, and if something is wrong, it just gives you an error, which is much better from our point of view as the ones who are implemented, and also probably from a user's point of view, because you don't get anything that you didn't expect. Finally, if you specify anything but if none for IF, then it also creates a guest device along with the block tree, which is not very nice because block layer and block devices are rather separate inside of QEMU. So you probably want to use different parameters, different command line parameters or QMP commands to specify the two. Also, it's better to specify all the options with a dash device for the guest device. Now, if you use if none, then that too is an issue because it creates a block backend. Also, it's kind of a hack in everything, but first and foremost for you, the important thing is that it creates a block backend, and then you have to worry about it. Because you would have to give it a name, you would have to give it an ID, and then you would have to manage it and carry it around, and that's just not good for you, and that's just not good for QEMU either, because then we have to worry about the user having a reference to these internal objects, and that's just not nice overall. So dash blockdev and device just create it automatically. So there you don't have to worry about, we don't have to worry about it. That's great. With dash drive, we do. So just don't use dash drive any longer. Now, for runtime configuration, we've already seen blockdev-add, which is a form of runtime configuration. And blockdev-del is just the counterpart to that. You can use it to delete trees you've created with blockdev-add again. There are some details on that. I won't go further into it, but if you want, you can, of course, read the slides later on. And the more interesting part is graph manipulation, because that's, in a sense, it's new. Blockdev snapshot, and especially blockdev snapshot sync, are not very new, but these are actually older kinds of graph manipulation we already have. Let's say you have these two block trees, which are just very simple. You have some file node at the bottom and some QCOD2 node on top. So a very simple chain to interpret a QCOD2 image file. And now you want to attach the right chain as the backing image of the left chain. So what you would need to do is you attach the right QCOD2 image as the backing child of the left QCOD2 image. And you can do that just using blockdev snapshot and create this connection, and that's it. So this is already one form of graph manipulation, but it's very limited. You can only use it to attach backing children, and you can only use it for backing children, and you can only use it to attach them. So we want to have something more flexible, of course. So what we've begun is called xBlockDevChange. It's called xBlockDevChange because it's still very much experimental. But you can also use it to add and remove children to or from a block node. Currently, that's only possible for Quorum, but that's pretty much the same as what blockdev snapshot does. It attaches a node as the backing child of another node. This would also allow it to remove the child again, but unfortunately, currently, it's not implemented for backing children, but only for Quorum. Now, the thing is that most children are not actually optional. So Quorum supports any amount of children. You can freely attach and detach children. It's just some duplication driver. So in the most simple case, it will just hand down requests from its parent to all its children, and that's all it does. But for instance, a QCOD2 file always needs its file child. It cannot function without because it needs some way, some place to store its metadata, some place to get its metadata from. And that's how most children are. You cannot detach them and attach them at will. So what we actually would want is node replacement, so that you say you have some filter node and you want to attach it between a QCOD2 node and its file, then that would mean that you would basically need to replace the file by the new filter. We'll see an example of that in a second. Especially for this use case, we also have a new proposal by Manos on the upstream list called blockdev insert node and blockdev remove node. And these commands would do exactly that. You could use them to insert filter nodes into a chain or remove filter nodes from a chain. Let's just look at an example because that will make it easier. So here's what I was talking about. You have some parent node and some child node, and you want to put a filter between the two. Now, this is not a situation that's actually possible because usually the filter node will require a file child beforehand. You cannot just create it without any child. Just like a QCOD2 node, it will always require a child node. So this is actually the situation you start with. You have parent and child, and then when you add the filter node, it's already connected to the child. And now blockdev-insert node would just do this. It would put the filter between parent and child, which is what we want. But basically, what you can see is all it does is replace the child by the filter node and nothing more. So we can see that, and blockdev-remove node would just do the opposite. So you can see that this is actually just node replacement with various constraints on it, which on one hand is good because you know if you do this operation, you will always only insert a node because it gives you these constraints and will arrow out if they're not met. But on the other hand, it means that for every use case of node replacement we would always have to create new commands. So we're still in kind of a discussion whether we want this one single command, xBlockdev change, which does everything, which does every node replacement, or whether we want to have a multitude of commands which can be used for everything you want to do. Now, besides this explicit graph manipulation, we also have implicit graph manipulation. So whenever a block job completes, it will do something with the graph, or most block jobs at least. For instance, the mirror block job will replace the source node with the target node because that's what it does. You copy the data over to the target, and then once you're done, you replace the source with the target and thereby continue using the target instead of the original file. Commit and stream depend on what they do. It's details I decided to leave out here mostly because it made the slide very full. And the issue with that is if you want to have control over this whole graph, if you actually created it from scratch with all the options and so on, you probably don't want this implicit manipulation. You probably want to know exactly when what manipulation is going to happen. So we're currently discussing, or there have been some RC patches on introducing an option called persistent for now. Maybe it gets renamed later, I don't know, to prevent block jobs from automatically exiting and automatically doing this graph manipulation. So the block job runs, it completes, and then it would linger around basically as some kind of zombie, and you would then call another explicit command to delete or to reap the block job, which would then result in this graph manipulation synchronously done, so you know exactly when it's going to happen. And speaking of block jobs, they are actually going to have filter nodes now. So for instance, the old mirror block job looked like this. You had some abstract block job object, which had references to two block backends, one pointing to the source and one pointing to the target. And then the data was copied over from source to target. Now it looks like this. You have some explicit mirror node above the source, and still these two block backends which point to both the source and the target chain, and the data gets copied over. So now we have this implicit node. And I hope that in the future it will actually look like this, where you have some mirror node that basically does all the work, and you just have the block job which only references this one node, and this node actually does all the work of copying source to the target. Let's see how far we can get with that. But the thing is that if you specify all the options and you want to have full control over the whole block graph, then you probably want to have control over this too. So now you can actually name this node that's introduced, which is also a way to detect whether this node is introduced, because at the same time, the mirror job was given the option of naming this node. And you probably should do so, so that you can later identify it and do things with it. And with that, my part is done, and I'll hand over to Kevin.
Right, so we have seen quite a few things in the block layer, mostly about the nodes, but there's more going on in the block graph. And that's specifically with op blockers. As they used to be called, it's now a bit different. But let's start at the beginning. So Max showed us quite a few users of block nodes already. One of them are the parent nodes. We have the block backends, and we also saw block jobs. There are a few more users that happen in practice, like just QMP monitor commands, for example. Or we have an MBD server within QEMU, which accesses nodes. And the thing is, not all of them don't work very well together. So if you use two of them on the same node, they might conflict in some way. For example, if you have a guest device which uses a node as its hard disk, that guest probably doesn't expect something external to modify its disk. Except if it's using a cluster file system, maybe it would work, but in the most common case, it doesn't work. Also, most block jobs create some kind of bitmap or something at the beginning, and currently they don't support to resize a node while they are running. This is just missing in the implementation, but just currently those are not compatible. What else? Yeah, if you have a commit job and you commit down across a few nodes to the backing file, you commit down the newer data to the backing file, several layers below it. The images in between don't make any sense anymore because they will present some data that is a mixture between the old state and the newer state that we're committing back. So while we could, in theory, let all these things run on the same node, it doesn't make sense. They're conflicting. And we want to protect against that. So the very first thing we did was we introduced a simple flag at each node, which just told, this is in use, don't touch this. And actually, I think I just skipped some slides. So if we start a merge job, we set the flag in use. And then if we say in the monitor, I want to resize this image, the resize command would first check, is this image in use? If it's in use, we don't do it, we return an error. And well, there's no conflict. So we set this in use flag for everything that we thought might conflict with each other. So we're usually blocking too much because some of these operations could actually be compatible. But if it's conflicting with a different operation, we just have to set the in use so that this is protected. So we're too restrictive. And at the same time, some things were not protected with the in-use flag, like guest devices, because if you can't use an operation while the same image is used as a guest device, that makes the operation completely useless. So at the same time, while it's too strict, it's also not strict enough. So it wasn't the optimal solution. Next thing we did was, well, then we'll just distinguish different operations and tell for each one separately whether you can do it now or whether you can't. So, for example, the resize would be an option, and other operations such as doing a block job would be a separate operation, and they could be blocked and unblocked separately. So when the mirror block job starts, and it wants to protect against resizing because it just relies on the initial value. It stores it internally, and it can't handle a resize of the disk. Then it can just set the resize blocker, but leave, for example, the commit blocker unset. So you could still do a commit block job at the same time. So resize would still check whether the resize blocker is set and would fail appropriately. And a different operation could still succeed because it's using a different blocker, because it's, well, we have blockers for each separate operation. In practice, this didn't quite work out because it means that every place that needs to be protected needs to know which other operation conflicts with it. And this also means it needs to know about all operations that even exist. And if we add a new operation, we have to amend all of these places, which we never did in practice. In practice, we just block everything. So we were back to the old state. Was not quite what we wanted to achieve with the system. Also, the op blockers were usually only added for the root node. So that's where we protected things. because most monitor commands only work at the root. So it's not quite how the block layer works today. We need something different. And the different system that we're using now is basically a permission system that we have built into the graph. It's now a core aspect of the block graph. And it works this way. You just define a set of low-level operations that you need, and you define a set of other of the same kind of low-level operations that other users can use while you're active. So we have a small set of operations, of low-level operations that you can use for permissions. And that's basically, I want to write, that's the most important one, I want to write to a node, and I can tolerate writers to the same node. We also have resize. We have a consistent read, which is, well, you can read from a node without having the consistent read permission. But consistent read means that the contents of the image actually make sense. So that's exactly the case with the commit job that I mentioned earlier. So the intermediate nodes of a commit job don't allow anyone to do consistent reads from it. So instead of just being tagged on the nodes, like the op blockers before or the in-use flag, this is made a mandatory core concept. Because in the old system, it was easy to just forget to block operations or to forget to check whether someone else is using the node, and that could be conflicting. So now it's a mandatory core concept. When you take a reference to a node, when you're attaching it to something, you have to specify which operations do I want to do on this node, and which operations can I tolerate that others do on the same node while I'm active. And this is actually checked. So if you write to a node without getting the right permission first, you will crash. We do assert that the permissions are taken. So you're actually forced to say what you're doing, because you can't get a reference to a node otherwise. You can't attach a node to a different node when you don't say explicitly what permissions you want and what you can tolerate from others. And if you give the wrong set of permissions, there are chances that assertions will catch it and you will crash. So this is much harder to forget to actually use, so it becomes a core concept. Also, the user almost never needs to do anything about that. Because QEMU already knows, like for example, if you have a format driver node, which accesses the image file node, QEMU knows what the format driver will need. So the user doesn't have to specify what kind of permissions it needs. Because that was an idea that that came up when in the context of image locking, that users would specify on each node what permissions to take. And that's not necessary because QEMU knows about it. There's only one case where QEMU can't know, and that's guest devices. Because it depends on the guest, really. The guest could be OK with other processes writing to the same disk in the background. For example, if it's running a cluster file system. But usually the guest isn't OK with it, and so that becomes an option of the common block devices like regular block. You get a share read write property, and you can set it to on if you want to allow sharing. So let's do this at a concrete example. This is just a simple block graph disk and a backing file like we had before. And now we have the permissions on all of the edges. So if we start on the left top, our root.io block device wants to read from the disk and wants to write to the disk. And it can allow others to read, sure, no problem. They can also resize because root.io block reacts to resizes, so it communicates it to the guest, so that's okay. But it doesn't allow usually others to write to the image because we have said share equals off. And then the permissions basically propagate through the graph, but they do change according to the node, to the requirements of each node. For example, the QEMU driver will need to resize the image because it's a sparse format, so the image file might grow. We require to resize. The backing file we only need to read, no problem there. We can't allow others to write because it will modify the data that we're seeing. So for example, if we're going to add a second root.io block device, this won't work because a second device wants to write to the same node, and we said we don't allow others to write to the same node. We can make it read-only, still doesn't work, because the first one wants to write, and we have share equals off on the second one as well. But if we make both read-only, then we can add that. Or we can say we share it. In that case, what actually happens is that root.io block says, if someone else writes to this image, that's OK. As you see on the bottom, the disk.file still cannot be written to by another process because QEMU can't tolerate anyone else. Because of its metadata, it would cause corruption. But the backing file is now allowed to be written to as well. So I could attach something there. Attaching the second root.io block just works fine now. So why would I attach a second root.io block? It doesn't make a whole lot of sense within one process. But we have image locking, which extends this across several QEMU processes, which means that we use POSIX locking. No, we use open file descriptor locking. POSIX locking isn't quite enough. That is relatively new in Linux, but it works. So we propagate these the permissions into locked bytes in the image file so that a second QEMU process will see the same. And then if I start a second QEMU process accessing the same image, that's basically the second root.io block node, root.io block device that I just had. And then it actually makes sense, and it will prevent this from happening. So if things go wrong with locking, first try if you have set the share read write property correctly. If you haven't, well, that's probably the cause of your failure. If that is set correctly and you get errors from the permission system, you're probably doing something dangerous. In some cases, you might decide that I'm doing only a read-only access. I don't care if someone else is writing. I know I might get corrupted data. It's not that important. Then you can use the force share option for block nodes. They don't remove the permissions that you take, but they force they force basically the node to tolerate any other access, no matter what the parents of the node actually requested. And if all else fails, you can use the locking equals off option for file nodes. so far, I haven't seen a single use case that actually needed this. Okay, and third part is kind of a summary. So what should management tools actually do now with all the changes that we made? We had the block backend names. Well, don't use -drive IDs anymore. You have node names, you have device names. In QMP commands, use, well, all commands that previously took block backend names, that is, drive IDs. They either take node names now, or they take, if they're more device related, they take QDIF IDs. So use that. Also, stop using -drive at all. Use blockdev instead. Filter nodes. We can get filter nodes automatically. Make sure that you manage them manually, because if you don't assign names, for example, manually, you won't be able to manage that part of the graph. You won't be able to even address if you want to change something at that point in the graph. Try to use, for example, the IO throttling filter node instead of using the old -drive throttling options, because the -drive options will create an automatic node, and you don't just have the control over it that you want to have. Same thing for block jobs. Block jobs insert filter nodes, and well, you want to manage them, so give them a name. Also, once we actually implement the explicit job deletion, make use of it, because otherwise you get surprise changes in the graph, and that will be really nasty to manage, especially if you're doing other graph manipulations like inserting filters, which, as Max told us, is really two steps: creating the new filter node and then inserting it into the existing edge. And that could lead to race conditions if you have automatic block job completion and it does surprise changes to the graph. So do things manually. And finally, the permissions. Well, just avoid dangerous setups if you can. Make sure that you set the share, read, write property correctly. Avoid the other two options that exist if you can at all. And if you must, then prefer the force share node option, because that's at least doesn't turn off the locking completely, so it still guarantees, gives you some safety at least. It's not good, but at least some safety. And well, if you must, you can turn off locking. As I said, I have so far never seen a case where this is really necessary. So if you think you must turn off locking, think twice. And that's it. So any questions? In the back.
I have two questions. So the first question is, do we recommend the user use the node name instead of the field name to specify their target? And the second question is, we have dry mirror and dry backup, and we also have block dev mirror and block dev backup. So do we plan to replace one by another? Or if not, which one is recommended to the user? Thank you.
Okay, so for the second question, yes, block dev backup is the new one. The issue with drive backup is that it just takes a file name again, and that it all does everything automatically, creates the file, opens it, and everything. Whereas with block dev backup, it's your responsibility to create the file and then open it in QEMU. So that's the more modern way to go forward. And I think in QEMU 3.0, we're thinking about deprecating drive mirror and drive backup. And the first question was about node names for, I didn't quite get it. Was node names for a target node from the mirror operation, or?
So we can specify our target by both node name and the file name, right? So which one is recommended to the user?
You specify the target by node name in mirror, or?
We can specify the target
Yes?
with node name or
Yes.
file name, right?
Yes.
So which one is recommended?
Well, blockdev backup is recommended, or using the node name always is now recommended. If you, like everything you specify in the block graph should be specified using the node name.
Okay.
And if you specify something on the device level, then you would need to use the QEMU path to the device, or the ID of the device. But everything in the block layer should now be specified using the node name, if possible. And if it's not possible, it's probably a bug, and we should fix it.
Yeah.
Okay, thank you.
Should we honor to change the approach for image management path? Right now we have QEMU IMG, which is doing most of the work. Maybe it would be wise to move image management to libvirt level and start QEMU process to perform actual block operation if there is no VM running. If there is VM running, the operation will be handled by already running QEMU.
Did you get that?
So you want you said you want to move the management from QEMU to that application?
No, they have QEMU IMG, which is doing a lot of work.
Yes.
It manipulates images, but with locking, this becomes a problem. And it's good that we have those problems because this allows images not to be corrupted.
Yes.
But maybe we need some automation in libvirt, which checks that there is no VM running. If there is no VM running, it starts QEMU process and dedicate image manipulation routines there.
So you think instead of the permission system in QEMU, libvirt should already be doing that, right?
We should have permission system
Yes,
in
they
images. It's very good that we have it.
They do, but it's not enough because in many times that we saw a corruption reported. The reason was that while the VM was run by libvirt, someone else used QEMU IMG manually on the same image. Okay, and that just broke the image. So we needed something on the QEMU level so that QEMU IMG would already refuse to touch an image that is in use by libvirt. And libvirt can't do anything about it.
Yeah, I understand that. I propose to move, I want to discuss moving of management layer image manipulation routines to libvirt level and provide similar functionality in version instead of running manually QEMU IMG, because it's dangerous, as you have said.
Well, yes, that would be preferable, but users still use QEMU IMG manually, so that's the reason why we had to implement it.
Yeah, I think even if you provided a way in Verge to actually do these things without using QEMU IMG manually, users are used to the way they're doing things today. They will keep doing this. So even if we did it, I think it wouldn't fully solve the problem.
Okay, thank you. So we are out of the time, so any questions
Yeah, thank you.
directly with the speakers after.